Uh, Today, we'll continue from where we left in the previous session, where we talked about conditional probability. Let me share my screen so that you can see what I have. All right. So this is where we were. We were talking about conditional probability, and we also established that when we say A given E, where E is an event, A is of course an event, we said, look, A given E is not an event. Uh, what we're doing here is we are defining what is called as a probability function. That is, uh, it's like saying, look, I'm defining a probability function given E. That's what it means. Uh, so be very clear that A given E is not an event. All right. This is something that we touched upon in the previous session as well. Now, let's solve this problem. This is where we left. We'll continue with this problem. Sorry, give me a moment. Yep. Okay. Now think of the whole rectangular box as the sample set S, and B is an event. So this B is an event within the sample space. And what we are doing is we're dividing the whole sample space or a sample set into 6 different events called A1, A2, A3, A4, A5, A6. Question number 1. Are these 6 events A1, A2, A3, A4, A5, A6 disjoint? Just have a look at the image and tell me. Are these
Yes.
events disjoint?
Yes, yes, yes.
All right,
Yeah,
of course,
obviously.
obviously, right. But why are they disjoint?
Common, there's no common among any.
Exactly. There's nothing common in, right? Because it's clearly evident that you take A1, A2, A1, A3, there's nothing in common between them, all right? The next question would be, if you look at this portion, can we say this area, I don't want to use the word area, but let's say this set, can we say this is B intersection A1? Why? Because the whole thing is B, this thing is A1, so we can say this is B intersection A1, B intersection A2, B intersection A3, B intersection A4, B intersection A5, and B intersection A6. My next question would be, can we say B is equal to B intersection? Okay, let me put it this way. Take B intersection A1, B intersection A2, B intersection A3, B intersection A4, B intersection A5, and B intersection A6. Are they disjoint? Yes, it is, right? Why? Because if you take this space and this space, there's nothing in common, between this set and this set, or this set and this set. Take any pair, for instance. There's nothing in common between them. All right, so which means they're disjoint. Now, can we say the set B or the event B is a union of B intersection A1, B intersection A2, B intersection A3, B intersection A4, B intersection A5, and B intersection A6? Can we say that? We can, right? Why? It's evident these are disjoint. So I
Disjoint,
can
yes.
comfortably say that B is the union of all these
Mm.
kuti sets. All right. Now, our final question would be, if I have to calculate the probability of B, okay, I want to calculate the probability of B. Each of these are disjoint events. B intersection A1 is a disjoint. I mean, you take B intersection A1, B intersection A2, B intersection A3, B intersection A4, all the way to B intersection A6. They're all disjoint events. My question is, when you calculate probability of B, how do you express probability of B in terms of these probabilities? How do you express that? If each one of these is disjoint, if each one of these or other, when you put them together, they're mutually exclusive or disjoint, how do you express probability of B in terms of these disjoint events?
Uh, sum of probabilities of B intersection A1 plus B intersection A2
Okay, I want
plus
to hear
B
from someone
intersection.
else. That's Abhinav, but is there someone else with a different view? Okay, someone else. Why? Let us say what Abhinav said is correct. Why is it correct?
Because these are mutually exclusive, right? So intersection will be 0.
Correct. So this goes back to the basic definition of probability. Remember, folks? Look at this.
P of A plus P of B minus P of A intersection B.
Correct. So if there's no intersection, then we can say that P of A union B is P of A plus P of B, right? So it's something similar here. So here you go. We have defined B as a union of these mutually exclusive events. So which means probability of B is probability of B intersection A1 plus probability of B intersection A2 plus probability of B intersection A3 all the way up to probability of B intersection A6. Okay. Now let's take one such example, probability of B intersection A1. Can you help me express this as a conditional probability?
Probability of A1 given B.
Okay. Is that so? It stops there? Okay, let's go to the definition
Into
of
P of
conditional
B. Into
probability.
P of B.
Exactly, right? So here's the definition of conditional probability. So we know that A given B is AB. So when we say AB, we mean intersection by P of B. So which means P of AB is P of A given B multiplied by P of B, right? Okay. So Mugundan, so what were you saying? So let's take this example. P of BA1. So when I say BA1, I mean B intersection A1. So what is P of BA1?
Like probability of B given A1 into probability of A1.
All right, that's one way. Can we also write it in another way? That's
Yes,
one
we
way to
see
write
like
it.
probability of A1 given B into P of B.
That's right. Both ways are perfectly fine. All right. Why? Look at this. You see this? Probability of AB is A given B multiplied by P of B, or B given A multiplied by P of A. Both of them are perfectly fine. All right. Okay. So you're right. So now I can express each of these as a conditional probability. I can express this as B given A1 multiplied by P of A1, B given A2 multiplied by P of A2, B given A3 multiplied by P of A3. Sorry, this is a typo. Let me change that. Okay. I can do that. Now this way of doing or calculating probability is called the law of total probability. All right. It's called the law of total probability. And this law of total probability will slowly lead us to what is called as the Bayes theorem. Okay. We'll come to that in a short while. Give me a moment. Now let's go to the next slide. So we're going to solve a problem, a simple one. Wait, let me just. Give me 1 minute, folks. Okay, now let's look at this problem. There are two problems here, but let's start with the first one. So there are two boxes, B1 and B2. B1 comprises 2 red balls and 4 black balls, and B2 comprises 4 red and 1 black ball. Okay. Now the first problem we're going to solve is the following. A box is picked and a ball is drawn. So there are two boxes. You pick a box, they're equally likely in the sense that you could have picked any box with the same probability, and a ball is drawn. What is the probability that the box is B1 and the ball is red? What is the probability that the box is B1 and the ball is red? That's my first question. Take your time. There's no hurry. Let me also put something on Excel so that we understand what we're talking about. Folks, you might get the answer, but it's very important that you do it the axiomatic way, which means define the events properly. That's extremely important. Okay. So let's say B1 is the event. Box 1 is chosen. B2 is the event where box 2 is chosen. Okay. Now, first question, let me ask this. Probability of B1, what is it?
1/2.
1/2. Okay, 0.5. Probability of B2?
0.5.
0.5. All right. Okay. Now let's look at this statement. Okay. The box is picked and the ball is drawn. Okay. Now, let us say you pick, let's say you pick B1. Okay. Can somebody tell me what is the probability that the ball will be red?
1/3.
Okay, why is it 1/3?
Okay, let me put it this way. There are, each ball is likely to be picked and red is 2. So the weightage of choosing a red ball is 2 in 6.
Okay, 1/3.
So
So I'll keep it as 2/6. Okay,
yeah.
you're right. 1/3 is right, but just to why do we say it's 2/6? If B1 is picked, there are 2 red balls there and 4 black balls. So totally there are 6 balls. Each ball is equally likely to be picked. So which means the probability of picking a red ball is 2/6. All right. Now, my question is from a notational standpoint. Okay, is 2/6. Sorry, is this 2/6? Is this P of R? Sorry, is this
R given B1.
or is it P of R given B1?
Probability of R given B1.
Okay, why?
Because we know that it is box 1. From there, we are finding probability of picking the red ball.
Okay, anybody who has a different answer? So Sirisha says 2 by 6 is P of R given B1. It is not P of R. You understand why Sirisha says so? Because if you look at the statement, it says a box is picked and a ball is drawn. So when you calculated the probability of 2 by 6, what were we doing here? You had already decided that you had picked B1, the box B1, and then you are picking the ball. So which means it's conditional on choosing the box B1, right? So P of R, okay, let me put it here. Is equal to 2 by 6. Now, look at the question. What is the probability that the box is B1 and the ball is red? How do you frame it in notational terms?
Intersection.
Probability of B1 given R. No?
Read it again. Had
Probability.
that been the case, my question, I'm still looking at the first question, okay? What does it say? What is the probability that the box is B1 and the ball is red? It doesn't say given the ball is red.
B1 intersection R.
Exactly, right? So this would be probability of B1 times R, okay? All right. How now, given this information, can I write this in a form that will make use of this, whatever I already have? Can somebody help me with that? How
I
can I
think we
write?
have to find probability of R also, right?
Why? We don't need to. Why?
This is
Can I say this is same as probability of RB1? Why? Or we know that probability of A intersection B is same as probability of B intersection A. No difference, correct? Now, how can we expand this? RB1, use conditional probability and expand this.
P of R given B1 by P of B1.
Is it by, just check.
Oh, sorry, into.
All right. So Sirisha says this is P of R given B1 multiplied by probability of B1. Anyone here who doesn't get this? This is the definition of conditional probability, right? We know that P of AB is P of A given B multiplied by P of B. That's precisely what we're doing here, right? So now we know R given B1, it's available here. We know probability of B1, which is 0.5. So which means this is 0.5 multiplied by all right, folks. Is it clear so far? Okay. Now let's look at the second question. Before you answer the second question, read it once. What does this say? This says a box is picked at random. You don't know which one, you don't know which box has been picked. And a ball is drawn. So you've drawn the ball from the box. You don't know which box it is, but you found that ball to be black. Okay, you found the ball to be black. Now I'm asking the question, what is the probability that the box was B1? Okay, now before you solve the problem, what does your intuition suggest? Which box has a higher probability? Before we sit down and start solving the problem,
B1.
Why?
B1.
4 black balls are there.
Exactly. Correct. So intuition suggests there is a higher chance that it was B1, which was the box that you could have picked. The probability of you picking the box B1 is much higher. Okay, that's what intuition suggests. So let's do this whole thing mathematically. Okay, let's do it step by step. We'll use the law of total probability, but we're already using Bayes' theorem here. Okay, though we haven't formally defined it, but let's take it step by step. So what do we need? We need probability of. Now we've defined all our. Okay, wait. I'll add some more. I'm going to call B as event where the ball is black. Okay. Now, what do we need here? Tell me in terms of conditional probability, what is required? Let me just copy this so that. Sorry. Why doesn't it copy? Oh, why? Thought it should copy. For some reason, it isn't. I don't know why. Okay, anyways, have a good look at this, folks. Or let me just snipe it. Or rather snip it. Snipping tool, not snipe. Snip. Here we go. Okay. The first question is, first things first, let's clearly formulate the problem. So what are we eventually trying to calculate? Probability of what?
B1 given B.
Sorry, say that again.
B1 given B.
B1
Given
given B.
B.
Do people understand? All right. Okay. Now, so let's go back to the definition of conditional probability. B1 given B is what? Probability of?
Box 1 given that the ball is black.
Now, we know, right? A given B is what?
B1 intersection B by probability of B.
B1B
By
divided by P of
B.
B, correct? Is it clear, folks? This is basic conditional probability, right? Now, I'm just going to make it a little different, where I'm going to say this is B1 divided by P of B. Okay, sorry. Can I do that? Sorry, let me just do single quote here. All that I've done is B1 intersection B. I'm writing it as B intersection B1. Okay. Now, can I write the numerator? Let's just focus on this bit. Okay. P of B, B1. Can I write this as P of B given B1 multiplied by P of B1? Can I write it this way?
Yes.
Why? It's simple, right? We know P of AB is P of A given B multiplied by P of B. So B given B1 can be written as B given B1 multiplied by probability of B1. Anyone who doesn't understand this, I hope you do. Okay. Now, of course, let's also start, calculating some basic probabilities. Wait. You know why we are doing this? Because it's easier to calculate this. Given the box, given you've chosen a box, it's easy to calculate whether the ball is black or not, right? It's so easy, right? So don't you see, can somebody tell me what is the probability of B given B1? Let me also copy
4 by 6. 4 by 6.
Let me just copy this as well so that so what is the probability of B given B1? B is of course the ball being black. So just look at this and tell me
4
what
by
is the
6.
okay 4 by 6. All right. So this is equal to 4 by 6. All right. Okay. Now, of course, I have the numerator is not a problem, isn't it, folks? Why? I have figured out that P of B B1 is P of B given B1 multiplied by P of B1. I already have these values available. Numerator, easy. Denominator is tricky now, right? How do I, now the question is, how do we handle the denominator? Now I'll give an example. It goes back to the whole idea of, you remember what we did here? The total probability. Imagine this B to be the B in the denominator. Okay, you're trying to figure out B. The challenge is to figure out B. It's not easy. So one way to figure out B is get an A such that the union of A is the whole sample set, right? And then what do? You write B as B intersection A1 plus B intersection A2 plus B intersection A3 plus B intersection A4, so on and so forth, right? Now the question is, what is that A here in this context? Can't we say it is the event? Don't you see B1 and B2? If you sum these two together, that's a sample set itself. Why? Because either you could have chosen box B1 or you could have chosen box B2, correct? There's nothing that you could have done, right? Now, are B1 and B2 mutually exclusive?
Yes.
Yes, okay. Let's do one thing. Instead of B, I'm going to call this BL so that there's little scope for confusion, okay? I'm calling it black, so BL. Sorry. Okay, B1 given black, because sometimes black. Okay, this is black. Okay, all right. Now, so we do agree that B1 and B2 are mutually exclusive, correct? Now, can we write BL, the black, as BL B1? When I say that, I mean intersection, of course. Okay, union BL B2. Can we write it that way? You can, right? It's something similar to what we did here, folks. No difference at all. What are we doing here? I somehow I get an A such that the sum of A is the sample set, right? I mean, rather, I get some disjointed events called A1, A2, A3, A4, A5, A6, such that everything put together is a sample set. Then I write B as B intersection A1, union B intersection A2, union B intersection A3, so on and so forth, because each one of them is disjoint, correct? I'm doing something similar here. I'm saying the BL is same as BL intersection B1, BL B1, union BL B2, right? Now can somebody tell me probability of BL? Can we say it is probability of BL B1 plus probability of BL B2? Can we say this?
Yes.
Why? Because BL B1 and BL B2 are disjoint. So you can comfortably say probability of BL is equal to probability of BL B1 plus probability of BL B2. Now we're going to figure out each of these. Let's start with probability of BL B1. I want to write this in a way such that it's easy for me to calculate. So how do I write it? Do I write it as BL given B1 multiplied by probability of B1, or do I write it as
First we have
B1 given BL? Which one is easier to write?
BL given B1
That's
into
easier,
1.
right? Because when you say probability of, you write it as probability of BL given B1 multiplied by probability of B1. It's easier to write because you have everything available. Don't you see that? BL given B1, here it is. You have it here. Then probability of B1, here you go. You have it here. All right. So this is nothing but multiplied by this. All right. Give me a moment. Did I did something? Okay, this is done. Now let's do probability of BL B2. Okay. How do I write this? Somebody.
probability of BL given B2 into probability of B2.
Okay. BL given B2 multiplied by probability of B2. So let's calculate probability of BL given B2. Let's do that. Okay. We already have P of B2. So we're going to calculate probability of BL given B2. Just have a look at this, folks, and tell me what is probability of BL given B2. I don't want Mukundan, Sirisha, and Abhinav to answer. Someone else. What's
1 by
probability of
5.
BL given B2?
1 by 5.
Sorry, louder, please.
1 by 5.
1 by 5. That's right. Correct. So this would be 1 by 5. Okay. 0.2. So now can we, I'll just multiply these two. Everything is available. BL given B2 multiplied by probability of B2. Okay. Now we have all the pieces available. So if you look at the formula, so what was the formula? The formula was this. The numerator was this. Sorry, where's the numerator? We said, yeah. Okay, so we need, give me a moment. Okay, let me. So probability of BL. Now, can somebody tell me what is probability of BL?
13 by 30.
0.4.
0.433.
Yeah, basically you sum this up, correct?
Hmm.
All right. So now what we need is, if you look at what we need to calculate. Somebody has to go on mute. I hearing some noise. Thank you. All right. So what do we need to calculate? We need to calculate this B1 given BL, which we have figured out to be this. We already know BL, and then BL B1, we've already calculated it to be this. So don't you see probability of B1 given BL would simply be this number divided by this number, 0.769231. All right. Remember, folks, what our intuition suggested? We thought that, look, the probability that the ball came from box 1 was much higher as compared to the probability that the ball came from box 2. All right. I'm going to ask a question. Without solving, uh, let us say I am calculating a probability function given BL. Okay. Given BL, which means given that the ball is black, I am calculating a probability function. Now, can somebody tell me what are the outcomes for which I'll calculate this probability function? How many outcomes are there in this case?
2.
2. Okay. So if you look at it, so one would be B1 given BL. And the other is B2 given BL. Only two possibilities, right? Because we know that the ball could have either come from box 1 or it could have, I mean, the black ball could have come from box 1 or could have come from box 2, correct? And given that there is nothing else, if you go to the basic axioms of probability, what should the sum of these two probabilities be equal to?
1.
1, all right? So the sum of these two should be equal to 1. So now, if I know this, I've already calculated this, right? B1 given BL, you see that? Then I don't need to calculate B2 given BL. I can just say this is nothing but 1 minus this. All right. Okay. Anyway, so what we have precisely done here is we applied what is called as the Bayes theorem. So the Bayes theorem is basically this, folks. This bit here, sorry, the Bayes theorem would be, give me a moment, I'll tell you what Bayes theorem is. Okay, I'll tell you. If I replace this with this expression here, this whole expression divided by probability of BL. This is Bayes theorem. Okay. Now, effectively, what we're saying is Bayes' theorem allows you to flip the probabilities. Okay, we are used to working with probabilities where, let's take the box example itself. You choose a box and then you choose the ball. Easy to calculate probabilities. What Bayes' theorem allows us to do is it allows us to flip it, in the sense, given that you've chosen a black ball, what is the probability that the box was B1 or the box was B2? All right. That's what Bayes' theorem allows us to do. Now, it might sound very trivial. What's the big deal? But there are tremendous amount of applications when you dig deep into Bayes' theorem. Okay. Any questions so far? All right, then I'll formally define Bayes' theorem for you. And then we'll stop with that for today because I don't want to drag this for too long. So let's say there are two events, A and B. What Bayes' theorem says is P of B given A is P of A given B multiplied by P of B divided by P of A. Now, can somebody help me derive this? How can we derive this? Okay, let's put it again on Excel. Okay. So we need P of B given A. All right. And this is what we need to derive. Okay, now help me out. First step, what do we do?
Probability of B given A equal to probability of B intersection A by probability of A.
All right, next step.
Probability of B intersection A can be written as probability of
Can we say
A
AB?
given B. Yeah, AB. Yeah.
We'll start with AB, okay? All right, then.
Probability of A intersection B is probability of A given B into probability of B.
Probability of B.
By probability of A.
Right, divided by probability of A.
The same.
Absolutely. Now that's your Bayes theorem, as simple as that. Okay. Now, we'll take an example of how to creatively use Bayes theorem, because we actually did that in the previous, while solving the previous problem, we creatively used Bayes theorem and what is called as a law of total probability to get a meaningful number for probability of B given A. Okay. Now, can we say the entire sample space S, I can divide that into two disjoint sets, B and B complement? So B, I couldn't put the complement letter there or the symbol there, which is why that's an apostrophe, by the way. So can we say I can divide the sample space into B and B complement and they're disjoint? Can we say that? Can we?
Yes, yes.
We can, right? Okay. Now, I'm trying to figure out the probability of A. That's the objective. Okay. Can I say A is same as AB union AB complement? Why? I'm saying A is AB, which is A intersection B union AB complement.
Oh, so the AB and AB complement are disjoint,
Disjoint, correct?
and they add together to form a complete set.
A. So this is exactly similar to this scenario. The one that we saw here. No difference at all, right? Okay. Now, so I can write A as AB union AB complement, correct? So now, can I write probability of A as probability of AB plus probability of AB complement? Can I? All right. So now this I can write it as probability of, how do I write this now? I'll write it as,
A given
okay, A
given B,
given B multiplied by
P of
probability
B,
of B plus,
A
sorry,
given B dash,
correct, plus
A
probability
given
of A given B
B
complement
into
into
probability of B complement.
probability of B complement. That's right. All right. So this is what we did earlier as well. You know, when we solved the previous question.
VC, I have a doubt.
Yep.
But that is actually A intersection B the whole complement, right?
What is A intersection B the whole complement? Say that again.
We wrote A as A intersection B union A intersection B complement.
Right. Correct.
And we added those probability, but while expanding it, we have to, how can we know, separate it as A and B complement?
Which part are you? I mean, I didn't understand where exactly you have doubt. Say that again.
We wrote A as A intersection B union A intersection B the whole complement,
Correct.
right? And we added those
No, not
probability. Why?
A intersection B the whole complement. It's A intersection B complement. Okay, let me make it clear.
Oh,
A intersection B union A intersection B complement. This is what it is. Okay, let me, I'll just see if I can help here. Wait. So
okay.
let us say this whole thing is a sample space, okay? And then this is B.
Okay.
I'm going to bold it. Can we say this is B complement?
Yeah, yes, we see.
All right. Now, this thing is A. Okay. This box.
Okay.
Can I say this bit is A intersection B?
Oh, yeah.
And this is A intersection B complement.
Okay. Okay.
Can I say that?
Yes.
Because
Yeah.
this whole thing is A. A intersection B would be this bit here. So this
Okay.
part would be A intersection B. And this part is A B complement, A intersection B complement. Is that clear?
Okay. Okay. Good.
So can't I say A is the union of, I'm just going to write it as AB. So this is A, by the way, right? So can I say A is a union of AB and AB complement, correct?
Yeah.
And since these two are disjoint, we know by law of basic probabilities, when you have something, when you have two events that are disjoint, the probability of A, which is nothing but, so the way to do this is probability of A is probability of, in this case, AB union AB complement, correct?
Okay.
And we know that this is nothing but probability of AB plus probability of AB complement. Is that clear?
Yes, yes.
Meena, who was the one who asked that question?
Madhumita.
Madhumita. All right. Okay. Now, given this, do you understand how this came about?
Yes, we see.
All right. Good. Very good. Okay. I hope this this diagram helped. Okay. So what we have done here is we creatively used the law of total probability to kind of split PA into small chunks, and so that you can work out certain small those expressions. You would have information about those expressions, and then you can figure out probability of B given A. And this is something that we did in this previous example as well. In this example, no, sorry, which one? Yeah, in the second example, that's what we did. Where what we did there was we assumed that the black ball came from either B1 or B2, right? And B1 and B2, the union of B1 and B2, the two boxes, was a sample set. And then we did something similar to what you're seeing here. Okay, that's a creative way of using Bayes' theorem and what is called as a law of total probabilities. Okay, I'll stop here. We'll solve in the next session. We'll solve a very interesting problem. It's called the Bayes rate fallacy, for us to understand how exactly Bayes' theorem is used in uh, you know in the world of medicine. So we'll understand that. It's not very difficult to understand, but it's quite instructive. Any questions, folks? All right. If there aren't any, we'll stop for the day. We'll continue on Wednesday. Okay. Thank you, folks.